Hey folks, good morning. My name is Christian. I'm a software architect with the Intel. I'm very happy to attend the DPDK conclave this year as well, even though remotely. So I don't get to see all the nice pictures that you have in your chapel where you're sitting in. So anyway, thank you so much. So today we want to talk a bit about the smart switch use case. So essentially, how to use DPDK to make a data center smart switch, to make a data center switch a bit smarter. We'll give you an overview of this use case called data center smart switch, and we'll take a quick look at the pipeline, the data plane pipeline for this use case. And then we'll gonna look at how we implement this complex pipeline on the Intel IPUs. More specifically, we have an Intel IPU adapter E2100 that we used for this exercise. And then we also take a quick look at the performance of this pipeline running on this IPU device. IPU stands for Infrastructure Processor Unit. Essentially, it's a smart switch. It's a smart NIC. Other names in the industry are also DPU, Data Plane Unit. We use the IPU name for this part. So, taking a quick look at this use case, what exactly is the smart switch use case in a data center? As we all know, a data center is mainly made of switches and servers. And in order to make the data center smarter, we need to have smarter switches, we need to have smarter servers. Now, on the data plane side, we could use servers to do some part of the data plane, namely the more complex processing that the switch usually is not able to do. Or we could also focus on the switch. Obviously, we need to focus on both sides of the problem. Now, for this discussion, we look at how to make the switch smarter. And obviously that could result in some cost reduction if we don't use the servers which are usually expensive. If we don't use them to do the data plane processing, if we could do that on the switch, then that would obviously lower the pressure on the servers, and we can use the servers to run VMs and other workloads that are not basically fundamental data plane packet crunching, right? So usually a switch is a device that processes a lot of packets very fast, but the processing is simple. And that is also a consequence of the fact that the switch usually, although it has like a significant amount of internal memory, sometimes you can also add external DDR to the switch. But usually the tables are reasonably small versus what you could do on a server or on a smart switch where you could add more DDR memory and have bigger table, more tables. Um, you have CPU instructions. Usually, the switches are not programmable. Some of them are, but they are exceptions. And it's kind of difficult to program at a high level. You could use the P4 language if your hardware supports it, but still you tend to get into limitations related to what instructions and what actions, what programs can you actually put on a switch. So then all those processing workloads that require more complex processing would actually go on a smart NIC. So then a smart switch essentially is a switch that does things very fast and very simple, plus a bunch of smart NICs, right? We could equip some of the external I/O ports of the switch with some smart NICs, and then those smart NICs would do the complex processing that is involved sometimes in or pretty much every time in a complex data plane pipeline. although it's not going to work at the same speed as a switch, but it does the job because not all the traffic needs to go through this complex processing path. It's usually some of just a subset of the input traffic, and most of the traffic usually goes through the switch without going through these smart NIC devices. Now, there is this concept is like very live and kicking in the industry. Is promoted by some people. One of the great promoters of it is Microsoft. They have this smart switch use case, and they also documented publicly in this project called Sonic Dash. Sonic is a network OS. Dash is basically an extension to this to the Sonic NOS. And that essentially allows for some of these pipelines to be created, provides APIs, and provides like the um, specifications for the pipelines that need to be there on the smart NICs together with the switch in order to make the switch smarter. In case you are not aware about this project, I fully encourage people to go on GitHub on the SonicNet Dash project and take a look at the documentation folder. It's a very complex folder with a lot of information about things that could be useful in order to make a switch a bit smarter. So essentially, the processing, the data plane, instead of going on the servers, it's not going to the switch either, but it's going to the smart NICs that are part of the switch, and logically everything is part of the switch. So taking a look on the pipeline here of the data plane pipeline of this project that we call Sonic Dash, which is a more specific instantiation of the smart switch use case. This is not the easiest pipeline to explain. I'll try to do my best and do it quickly as well. So one of there are multiple use cases part of the Sonic Dash project. One of them is called VNet to VNet, and that's what we are going to focus on. It's essentially a virtual switch, and its purpose is to connect virtual machines that are geographically apart, right? They could be on different continents, but still we can create this abstraction that everything is part of a big, nice global data center, right? Now, let's say you have two VMs that are very far apart from each other. Each of them has to be connected to a smart switch, right? So think about two endpoints, two VMs, and on each side there is a smart switch. Now we can locate ourselves on one of these switches and say this is the local switch and this is the local VM, and then we have a remote VM that is some other part of the world, um, and that's also that's also connected to another switch, which is the remote switch, right? So it's about the two VMs talking to each other through these two switches, right? Obviously, in the middle there could be could be the whole internet with many other nodes and switches, right? So um, the main blocks here are essentially the flow lookup with connection tracking. So basically, one VM initiates a connection, it sends packets to another VM. That VM needs to reply back with the packet. So uh, yeah, we can focus on the TCP use case, which is more connection oriented as a protocol, right? Or we can look at a UDP connection. I think it's easier to explain it for a TCP connection. But before that, basically just to go through quickly through the main blocks, on connection tracking side, we try to discover new connections, right? And we want to basically register them in our database of flows or connections. At some point, we also need to forget about those connections. For example, when we have a timeout, we don't get any packets for a long time, for a reasonable amount of time on that connection. We need to delete it from our table Or in the case of TCP, there is also a graceful procedure to finalize the connection through the FIN sequence, right? So we need to detect that. So we try to monitor the state of the connection. We try to discover new connections, register them, but also we need to monitor the lifetime of the connection, see what happens with that connection. And we are like the man in the middle. We are not gonna run the TCP state machine. It's the endpoint VMs that are gonna run the TCP state machine. But we are a man in the middle. We are a switch, and we need to monitor the connection, right? Because if we don't monitor the connection, our table will fill up and will have a table full with many connections that are dead. So in order to reuse the table space, reuse the resources, the memory, and all the resources like meters, counters, anything else we might have in the data plane for a connection, we also need to keep track of what's happening after we add a connection and remove it from the table as soon as we can safely remove it from the connection, from the connection table or the flow table, right? And now, whenever we add a new connection, we also need to ask the policy if we are allowed to do that, because we are not going to be able to add connections if the policy says otherwise. So we have some ACL tables for each direction, outbound and inbound of traffic. And the specification says we need to have five level ACL tables for each direction. And also a special shout out for this feature, which is called high availability, which essentially is looking at adding redundancy for the data plane. It's pairing up two different devices, and it's looking at replicating the flows from one device to the other device. One is typically an active device, the other is a passive device that is simply not processing traffic, although it could, but traffic is not directed to the passive device. But every time the active device is discovering new flows, is adding new flows or removing some of the flows, needs to also notify the passive device. So basically, the flows are replicated from one device to the other. It's a very complex requirement. There are also some variations where both devices are actually active and they are paired up, so things can get very complicated very quickly. But it's one of the requirements that is a must-have for many of our customers these days. So although it complicates things, although it uses up bandwidth, because these data plane devices, these two devices that are part of the HA pair, they don't have a cable, a direct connection between them. They also have to communicate and replicate the flows through the switch, so that takes up bandwidth. Now, as I was saying, there are two directions. There is an outbound direction and an inbound direction. Outbound means that traffic goes from our local VM to a remote VM. So it basically forces us to decide where we are, right? And inbound is anything that is coming to us from some remote VM, right? Now, every time, looking for TCP, what happens is usually a packet comes in, and this packet could come from a local VM or from a remote VM. We are the switch, right? Or we are the smart NIC here. And then based on the MAC address, whether we know that or we don't know that, the MAC address is associated with VM, we can decide whether this is an outbound direction or inbound. Is it coming from a local VM or from a remote VM? And that's the traffic direction that we decide. We find out very quickly here at the beginning of the pipeline. Then we want to look up that flow into our database. So let's say we have a TCP SYN packet, right? Let's focus on TCP for a second. TCP SYN is the first packet of the connection. And then whenever we are going to look up that packet and see if we have that flow in our flow table. If we don't have it, we have to we say, okay, this is a new flow. It's a TCP SYN packet. We go and we look up the policy. We ask the policy if it's okay to add this connection. If the answer is fine, okay, go ahead. Then we add a connection. But that connection needs to logically cover both the forward flow, basically packets that belong to the direction of the TCP SYN packet, but also the reverse direction. Basically, we need to make sure that we are also going to be able to allow the response of like the SYNAC packets and all the other packets coming from the other side, right? So it's a bidirectional connection. It depends on how we implement that. It could end up with two flows in the table, or could be a single flow if we do some symmetric hashing. So yeah, it's important to know that only the policy is only looked up for the first packet of a new connection. We register the packet, then we monitor the state machine for the connection, and at some point we are gonna remove this connection. And now, obviously, there are some other blocks involved, like billing. We do have counters. We have overlay routing. We have underlay routing. The overlay routing is done. The lookup is done just for the first packet, and basically we store that result in the flow table lookup, right? And basically for every and for all the next packets belonging to that connection, either forward or reverse flows, we are gonna perform the overlay routing actions that we decided when we took a look at the first packet, right? Because all the packets will follow the same path through the network unless we have some ECMP involved, which is not a problem for this. So yeah, that's a very quick overview of this pipeline. Now let's look at the implementation. In order to implement this pipeline, we have our Intel IPU adapter E2100, and this some people are familiar with it. It's essentially a smart NIC, and you could look at it as like two parts. The left hand side part over here, which is the networking part, the networking let's say domain, the network processing. Side of the smart NIC, where we have our hardware pipeline, which we call FXP, flexible pipeline or packet processing pipeline over here. So this is P4 programmable. We can create many tables, we can have actions, we can connect things together through a P4 program. Now on the right hand side here, we have an array of ARM cores. We have 16 ARM Neoverse N1 cores. And we can look at this as the compute part of the platform. And obviously we have a DDR for memory, we have a 3 DDR for channels, and many other engines that like encryption, inline encryption, inline crypto, or look-aside crypto, and many others that we could use, but we are not going to focus on these today. Now, the way we implemented this is somehow counterintuitive. People might think that all the packets, all the exception, might think that only the first packet is processed by the ARM cores, and we can look at that as a sort of exception or not so fast path, like the slow part of the fast path or the exception path. That's not the case here. Because due to the complexity of the connection tracking requirements and due to the complexity of the high availability requirements, we decided to actually do the connection tracking, flow table lookup and connection tracking on the ARM cores. And then basically the hardware pipeline is going to do all the table lookups that it can do, with the exception of including the policy lookup, but it will not do the flow lookup, because there is a huge number of flows and the requirements are very complex for what we need to do with those flows. So then we do ENI and direction lookup, overlay routing, underlay routing, packet modifications, and also symmetric hashing and RSS. We use symmetric hashing to make sure that we don't have to register two flows and use two entries in the flow table for every connection. That will waste up space. And we have symmetric hashing, we have RSS here. So we use that. We play some very simple tricks to basically point the two flows forward and reverse to the same entry in the flow table. Also, keep in mind that the TCP state machine, for example, is shared by the forward and reverse flows. There is a TCP state a TCP state machine per connection, not per flow, right? For UDP is actually simpler. we only have to look at the timeout. Any packet could be the first packet. In order to add the connection, to remove the connection, we just have to look at the timeout, right? And essentially, we can say that the UDP connections are always in the established state. Established is a TCP state that where the data is transmitted, right? So a lot of the data path is on the hardware pipeline, the FXP pipeline, but the connection tracking is on the ARM cores. And as you could probably see, I mean, we have some SYN threads that only handle the TCP SYN packets to add connections, and we have worker threads, which are actually more threads than SYN threads at this point. And we do the TCP and UDP flow state update, the state machines, the aging part, keep tracking on of the timestamps there to see when we need to remove connections. The policy lookup is also could be done here, although the main use case is to do it on the hardware part. And we also add the UDP flows here. The flow table is actually shared between these two classes of threads, and we have two instantiations of our software. In the first one, there is a global table, but lately we moved on to basically slicing the flow table into many smaller flow tables that are owned by. There is a single SYN thread and a single worker thread that can access a slice of the global flow table. And it all boils down to the fact of inventing some smart data structures where you could have many threads, you could have multiple types of threads working at the same time on the same table. Some threads are adding entries in the table, while some other threads are removing entries from the table, or they are changing the entries in the table. And it's all about inventing some nice data structures that are also giving a good performance. We don't use logs, right? That's a bad word in DPDK. So that's why, that's the reason I'm saying we use DPDK to make a data center switch smarter, because the connection tracking is essentially a DPDK application running on the ARM cores. Yeah, I think I'm not sure I made this point clearly. I'll make it again. All the packets actually go through the hardware fast path, but also through the ARM cores. It's not just the first packet of the connection that goes to the ARM cores. It's all the packets go through the ARM cores. The ARM cores are on the fast path, in line on the fast path. So some people might say, hey, but that's going to kill your performance. And I'm going to say, actually, on the opposite, we are going to get a good performance. So what exactly is performance? Coming to the final point, to the last point on the agenda, how do we measure performance for the dash pipeline, for the smart switch pipeline? It's not about packet rate, it's about connection rate. How many connections per second, TCP or UDP, we can handle, right? There is we are working closely with our friends at Keysight, and they developed a procedure. We are using their hardware and their software to do the benchmarking, and they developed a procedure called hero testing for this project, which is documented as part of the project. So essentially, they want to see what's the rate to accept TCP connections, but they also want to see that when the device is under heavy load. So essentially, we already have 30 million flows that have to be set up on the device before we start the real test. So it's 15 million TCP connections and 15 million UDP connections that are all bidirectional. And we have to pre-establish those, and then we want to play with adding TCP connections, and they also have to be removed because the rate has to be at least 3 million connections per second on top of these 30 million that we call background traffic, and they have to be kept alive. So essentially, we need to handle packets for the background connections. We need to keep them alive, otherwise they will expire and they will get removed, and the test will fail miserably. And we also need to add more connections that are short-lived, because we need to measure the rate, we have to have short-lived connections that have to be added quickly, removed quickly as well. And we use like all these XIA cards to do UDP traffic or background UDP traffic, background TCP, and also the transient, the short-lived TCP connections, which we call the CPS traffic. And you can see the details on the slide here. It's a very complex environment, and it's all focused on adding rapidly adding new TCP connections while the device is under heavy load. It's a very tough test. And this is a screenshot with performance that we get from our XIA Keysight equipment, right? And there are many things here. We take a look at some of the TCP errors or retransmissions and all sorts of errors. You see, we don't have any errors here. So it's a very sensitive pipeline to dropping packets. If you drop a packet, that packet might be a SYN packet and the connection doesn't get created, or it could break the TCP state machine if you drop a packet, or it could result in a timeout because that connection is not kept alive. So you really want to have zero packet loss. This is a zero packet loss pipeline, ideally, right? And you can see here that our rate, I said it has to be at least 3 million connections per second. TCP new connections per second. We actually do twice as much, actually a bit more. We do 6.4 million connections per second, TCP connections per second. So that's a great result on the IPU, and that is actually our conclusion. Before I take questions, that on the Intel 2100 IPU, we can achieve a TCP connection rate of 6.4 million connections per second for the new TCP connections, on top of keeping alive 30 million pre-established TCP and UDP connections. Thank you so much, and open for questions.
Hey, Christian. Thank you. Great presentation. Question about benchmarking. Is it open source? Does it require XIA, or you can run it with some commodity hardware and some open source tools?
Is this Konstantin?
Yeah, that's me. Hey.
Hello, hi Konstantin. Yes, we use the XIA equipment. And there are some scripts here. Now, there are several card types that need to be used. There is this UHD, which is a switch. There is basically a single XIA chassis, right? And you have different cards. You have like Novus cards, and you have CloudStorm cards. And we use actually 3 CloudStorm cards, one for TCP background, and the 2 for the short-lived TCP, the CPS traffic. And now the scripts for these cards are, I think they are open source. Our Keysight folks are open sourcing their scripts as part of the Sonic Dash repository. You can find them there. Now, can you replicate the same for, let's say, with the T-Rex or with the DPDK traffic generator? Yes, you could do that. It will definitely be more work. You have to maybe use lots of servers to do that and create your infrastructure. Now, you could devise your packet sequence for TCP, like we use just 6 packets per connection. We gracefully terminate the connection for TCP. On UDP, obviously, we don't know when the connection gets terminated unless we get the timeout. But yes, obviously, you could do that, but there are no open source scripts that I am aware of for doing that with T-Rex or with packet chain.
Okay. Okay. Yeah, thanks. And then second question, remember you show this flow table, a table for flows, which is shared between 2 different threads, right? Between SYN thread and worker thread. Yeah, exactly. Is this part open sourced, or this yellow box in the middle? Okay.
No, this is Intel proprietary software at this point.
Okay. Do you plan to open source it?
We do have some patents pending on some of these procedures. We don't have any plans currently to open source it, unfortunately. So I cannot comment. It might happen at some point in the future, but currently we don't have any plans, as far as I know.
Yeah. Thanks again.
Thank you.
Hi, this is Nitin Saxena from Marvel. I have a question regarding the slow path processing. Is it on OVN?
The slow path processing.
Yeah, the overlay and the underlay routing, right? It is based on OVN or what?
No. Actually, this is basically the overlay routing, the underlay routing, all these blocks that show up on the FXP. These are basically tables in a P4 program that is loaded into our hardware pipeline. And this is basically a P4 programmable hardware doing these blocks. And we cannot run a high-level software on the FXP hardware, but we can only run a P4 program. So we need to specify tables and actions in P4 syntax. Now you could move these blocks to the ARM cores, but then you'll use up more ARM cores. So by the way, we use 12 cores. The performance numbers that I showed, the 6.4 million connections per second, is with 12 ARM cores. I think we have 2 scene threads, 2 ARM cores doing scene threads, and we have 12 cores doing worker threads. Now you could move more stuff to the software, but performance would be lower, much lower actually. You could use open source software where things might not be as fine-tuned, and performance would be even lower again. And you are going to use waste basically your hardware pipeline. You are not going to use it. So the answer is no. These blocks are on the routing is definitely on in the hardware. It's a very straightforward block that the hardware can typically do. Many hardware from many vendors. Yeah.
Hi, Christian. This is Jarin. So this is one of the pipeline implemented for Sonic, right? Because Sonic has a lot of APIs, right? So you're not implementing all of that, right? It's just one of the use case.
Now, Sonic, are you referring to the network OS, to the Sonic NOS? There are many containers there, and yeah, that's basically one of the next steps that we are working at to integrate this with the Sonic network OS. So there are many containers there that will have to fit on the ARM cores as well, but. Also, the data path is kind of part of that network OS, including the dash, right? Now, from the perspective of the network OS, this is just control plane code to update these tables, right? So basically, you want to add routes for overlay or underlay. You want to update the policies. The control plane will not play with the flows. It might want to debug the flows, take a snapshot of the table, the connections that are in the table, but these connections are created so fast and removed so fast that the control plane cannot keep up with. So that's why this connection tracking and flow table and connection tracking is done entirely on the data path without control path intervention.
Yeah. So if you see this traditional Sonic architecture, right, they're leveraging the SAI APIs, right? So
exactly. That's what we use. We use the SAI APIs to populate these tables. But that's all Sonic cares about is how to populate these tables and how to sync up these tables if you have high availability, and how to do that through SAI and various RPC mechanisms that I'm not an expert of. But Sonic will not care about the data plane, right? It assumes that somebody does the data plane for Sonic. Right?
This implementation, like all the SAI attributes / all the objects were implemented using DPDK, or it's just some set of it?
Given the fact that these tables actually go on the hardware block, the SAI API that is known by Sonic actually translates to a proprietary API that we use for populating the hardware tables, right? So it doesn't go through DPDK. And now it would be great, given the work that we did in DPDK, to add the prog action for programmable devices. What we could do is we could have an RTE flow layer to populate these tables, and then use DPDK to populate these tables. And I'm pushing on that, but for various reasons it got delayed. So we still don't have RT flow. So DPDK is not involved to populate the tables yet. But
so there is nothing DPDK there. It's all custom proprietary software, right? If I understood correctly. And P4, yeah, right?
P4 for the FXP, and this is on the ARM cores. Everything is actually DPDK. well, there is also an operating system on some of the cores, but yeah, this is DPDK running under Linux, right? But it's just that we don't have this open sourced. But it's still DPDK. It's not open source DPDK, but it's still a DPDK application. Everything is DPDK API.
Okay, so then one more fundamental question. So in this use case, traditionally people use with switch, right? The standard switch, right? So, but if you're trying to do this with the DPU/IPU, right? So one is performance per watt, right? And the latency. I think these two things may not add up well, right? As a POC or doing the functional level implementation is okay, but do you think it like we can make it as a real solution if you consider latency and performance per watt?
Yeah, power consumption is basically driven by the device rather than the application, I would say. And latency it might have some challenges because yeah, you have to go through the hardware pipeline, then you have to go through the ARM cores, and then go back to the hardware pipeline. But that's also under control. Now, can it be real? It is actually very real because you see, like performance is telling us like 6.4 is actually double than the requirement. And 6.4 million connections per second, and that's what matters. That's what performance means for this pipeline. Is not throughput is important, but throughput is obviously the result of how many packets you send for your TCP connections. How many packets you send them to keep the other connections alive. So you could actually do a math of the throughput that is required to get this rate. Now, obviously, in real life, the TCP connections might be longer lived, but the timeout might be also bigger. We use a very short timeout for TCP. It's actually 5 or 10 seconds for a TCP connection for testing purposes, because you want the test to finalize in a reasonable amount of time. But in real life, the timeout would be 120 seconds. So there are many things that vary, but this is not limited by throughput. It's actually limited by the connections per second you can do, and that's why basically this shines, right? If it would be an L2 forwarding application, and we would try to do this here to send all the packets through the ARM cores, then obviously the throughput would be much lower than we won't be able to sustain the line rate, right? We will get much worse performance than if we just route everything through hardware. But that's not the point here. We don't do forwarding. Forwarding is not the main point. It's adding, removing connections very fast, connections per second. It's a kind of different mindset than the traditional L2 forwarding in the DPDK, but that's what many customers in the data center want these days. So we also have to align and implement these requirements.
Okay, thank you.
Thank you.
All right, lots of good questions there. We're running a little bit behind. There's a break scheduled now, so thanks so much, Cristian, and let's take the break.